Deep beneath Yellowstone lies a sleeping giant. As recently as 640,000 years ago, this slumbering giant tossed and turned, its movement shaping the very foundations of the park. As pressure built far below the ground, the earth rumbled and shook before magma burst forth from below. A super eruption. 170 young volcanoes rumble and lie in wait across the United States, including Yellowstone, which is home to the world's largest concentration of geysers and one of the world's largest hydrothermal systems. These are fed by volcanic activity deep below the ground. Volcanoes have captured human awe throughout millennia. Their explosive power not only shaped the features of our world, but also the course of its history. Mount Vesuvius, Krakatoa, Mount St. Helens, and more recently Hunga Tonga Hunga Ha'apai are solidified in human memory, owing to their sheer destructive power. But compared to the might of ancient supervolcanoes, these eruptions were small indeed. Today, the Yellowstone Caldera is a scenic destination, through which winds the Yellowstone River, leading into the freezing Yellowstone Lake. Spanning roughly 70 by 50 kilometers across, geysers and hydrothermal features dot the landscape, heated by the raging heat of the fires below. Periodically, these geysers erupt with steaming hot water, and hot springs bubble away, teeming with life. But these are mere hints of the power that Yellowstone holds. Yellowstone's volcanic saga begins millions of years ago, when the first of the 4 calderas that make up the park was born. The national park itself sits atop of 4 overlapping calderas. The most well-known, the Yellowstone Caldera, Henry's Fork Caldera, West Thumb Caldera, and the Island Park Caldera. A type of geographic depression, calderas are the scars of super eruptions, as masses of magma are thrust into the atmosphere with such force that the surrounding land collapses into the now empty magma chamber below. Yellowstone Caldera, the most well-known, formed 640,000 years ago, following the Lava Creek super eruption. A resurgent caldera, Yellowstone is characterized by a broad volcanic plateau, surrounded by low cliffs that mark the border of the caldera itself. Within the boundary lies the resurgent dome, an area of land that has been lifted up by subterranean magma movements. This caldera is the Yellowstone volcano. Volcanoes are formed when magma rises, either at convergent or divergent plate boundaries, or within tectonic plates themselves at a mantle plume or hotspot. Collectively known as the lithosphere, these plates contain the Earth's crust and uppermost solid mantle. Their thickness and size varies greatly depending on the age and type, whether oceanic or continental. But despite their thickness, these plates are not stationary and move agonizingly slowly across the asthenosphere, the outer region of Earth's molten mantle. As they move, lithospheric plates eventually converge and encounter one another. Locked in a terrible struggle, the plates fight until a winner emerges victorious, and one plate sinks beneath another in a process called subduction. As the subducted plate becomes forced downwards, the heat of the Earth's molten core melts the rock, creating magma. This magma then wells back up into chambers or reservoirs where it feeds volcanoes. Called a convergent boundary, there are two ways for a volcano to form here. The first is when an oceanic plate descends beneath another, diving below the dark, crushing depths of the ocean and into the heat of the earth below. The second process of convergent boundary volcano formation is when an oceanic plate is subducted beneath a continental one. Oceanic plates are denser than continental plates, and this density means that when it comes to plate warfare, the denser plate is the loser, sinking beneath the weight of the victor. At divergent plate boundaries, these tectonic plates are diverging, moving away from each other. Their separation allows molten rock to rise to the surface, erupting as lava and creating new ocean crust. Finally, there are the hotspots, or mantle plumes. These hotspots are reservoirs of magma deep within the earth that well to the surface as columns. Sometimes referred to as intraplate volcanism, hotspots are not always in areas of subduction or at plate boundaries. As the tectonic plate drifts across the hotspot, it creates a chain of volcanoes, although the hotspot itself never actually moves. It is a hotspot that created the Yellowstone Caldera. Known fittingly as the Yellowstone hotspot, this mantle plume is responsible for a series of calderas that in turn created the eastern Snake River Plain and the region we now call Yellowstone National Park. Over 16 million years, the hotspot has shifted across the North American continent, beginning in what is now known as Oregon and Nevada. As the continental plate continued its slow journey west-southwest, the hotspot remained stationary, but appears to have moved further northeast, owing to the southwestward creep of the continental plate. Over millennia, this hotspot has created various volcanic eruptions, until the most recent one 640,000 years ago, when the Yellowstone Caldera was born. Volcanoes take many forms. The most easily identifiable and picturesque are the composite volcanoes, or stratovolcanoes. Picture Mount Fuji in Japan, with its snow-capped peaks bathed in clouds. Conical in shape and growing steeper closer to the top, these volcanic peaks stand high above surrounding mountains. Usually found above subduction zones, the summit of active composite volcanoes has a crater, which may contain fumaroles, crater lakes, or even glacial ice. The largest volcanoes on Earth are the shield volcanoes. Low-lying flat domes like Mauna Loa in Hawaii. Broad and wide with gentle slopes, these volcanoes are named for their shape, like a shield lying on the earth. Convex in shape, shield volcanoes are flatter near the summit. The third most common shape a volcano can take is the cinder cone, and these volcanoes are the most common type found across the world. With their steep, conical hills, cinder cones have a prominent crater at their summit, and are frequently found in volcanic fields amongst hundreds of their kind. Unlike composite and shield volcanoes, which are polygenetic, cinder cones are monogenetic, meaning they only erupt once. After their eruption ends, the vent's access to the magma source is blocked off by solidified rock and magma. Cinder cones and other monogenetic volcanoes are typically smaller than polygenetic ones, which can experience multiple eruptions. While these are the most common shapes and forms a volcano may take, there are others. Mars, spelt with 2 A's, tuff rings, domes, and calderas are all volcanic types as well. But there is another, a classification that has burst into mainstream culture owing to its sheer Armageddon-esque power. A supervolcano. Yellowstone is often referred to as a supervolcano, and the large-scale destruction it could cause has captured many an imagination. But supervolcano is something of a misnomer. To understand a supervolcano, we must first understand eruptions and how they are classified. When a volcano erupts, it does so in one of 3 primary ways. These different types or styles of eruption depend on the material and mechanics of the volcano, such as if there is water, lava, or ash. Perhaps the most iconic type of eruption is the magmatic eruption. If you're a visual person, this is likely what you see when you imagine a volcano erupting. Vibrant glowing lava flows shot into the air, ash clouds and gas stretching skyward, and intense heat. But the intensity and explosivity of magmatic eruptions can vary widely, depending on the amount of gas present in the volcanic system and the viscosity of the lava and composition of molten material. If there is a higher proportion of molten material to solid crystal, it means that the magma is more likely to mobilize. Magmatic eruptions can be described in one of 2 ways: effusive or explosive. Effusive eruptions are characteristic of low viscosity basaltic lavas. Low viscosity magma allows volcanic gases to escape easier, so that when they breach the surface, they do so as a lava flows. In the grand scale of volcanism, these eruptions are relatively gentle, but no less dangerous. When magma reaches the surface, it becomes lava, which can be slow or fast moving, depending on viscosity. Explosive magmatic eruptions are characteristic of sticky, viscous magma, filled with trapped gas. As pressure builds up, the magma eventually explodes out of the volcano. These explosive eruptions carry tephra and pyroclastic material, and can form deadly pyroclastic flows. Avalanches of volcanic ash and dust, these flows move like a liquid, flowing down the mountain and devouring everything in their path. These pyroclastic flows can reach incredible temperatures of up to 500 degrees Celsius. And when they solidify, they form a type of rock called ignimbrite. More explosive types of eruptions are hydrovolcanic or phreatomagmatic, as hot magma interacts with surface water or shallow groundwater. If the magma chamber drops below the water table, the groundwater interacts with the hot molten rock, causing steam pressure to build up and up and up until it explodes upwards. Producing steam and tephra, these eruptions are violently explosive, expelling masses of volcanic matter. Similar to phreatomagmatic, but lacking magmatic material, are phreatic eruptions. Sometimes heralding magmatic eruptions, these may include volcanic ash from shattered rock and are driven by superheated groundwater turning to steam. The visuals or style of magmatic volcanic eruptions are given descriptive classifications as well, based on the eruption styles of different volcanoes. The weakest are Hawaiian eruptions, which are effusive eruptions characterized by fire fountains and fluid basaltic lava. These lava flows can be as fast as 100 meters a second, covering the landscape with molten hot lava, but forming new land in the process. Named for the stratovolcano Stromboli, Strombolian eruptions are short but powerful. These explosive eruptions create fire fountains that can extend hundreds of meters into the air, raining down ash, volcanic bombs, and other volcanic materials. Sitting neatly in the middle of this classification system are the Volcanian eruptions. The term Volcanian was first used by volcanologist and Catholic priest Giuseppe Mercalli upon witnessing the 1888 to 1890 eruptions on the Italian island of Vulcano, which is known for its volcanic activity. These eruptions are intermittent, producing dark ash columns that rise to moderate heights. More explosive than Strombolian eruptions, Volcanian ones may also be phreatomagmatic in nature, though usually only small volumes of magma are present. The more destructive, volatile eruptions are named for Pliny the Younger, who described the destruction caused by Mount Vesuvius in 79 Common Era following the death of his uncle, Pliny the Elder. Plinian eruptions are sometimes called Vesuvian, owing to their origin with the famous volcano. Subplinian, Plinian, and ultraplinian eruptions have high viscosity magma that are rich with silicic materials. Extremely explosive in nature, Plinian eruptions produce ash columns that extend well into the stratosphere, spreading out into a wide umbrella shape. Thick pyroclastic flows are formed as eruption columns collapse under their own weight. Plinian eruptions may sometimes be accompanied by volcanic lightning. The luminous blue spears of electricity stark against the dark, roiling ash clouds and molten rock. The largest of all eruptions are ultraplinian. Their explosive power, called colossal, megacolossal, and apocalyptic. These eruptions are so immense that they exhaust their magma supply, the chamber collapsing into itself to form calderas. But while these terms describe the styles of eruptions, volcanic eruptions themselves are also classified according to a rating system, similar to the Richter scale for earthquakes. Called the Volcanic Explosivity Index, or VEI, it rates the destructive power of each type of eruption. Starting at 0 or non-explosive, the Volcanic Explosivity Index goes all the way to 8, ranked as apocalyptic. A super eruption is any volcanic eruption that reaches an 8 on the Volcanic Explosivity Index, discharging thousands of cubic kilometers of volcanic material into the atmosphere. At any given time, there are between 40 and 50 volcanoes erupting on Earth. 1,350 volcanoes have erupted throughout the Holocene. Sometimes called the Anthropocene, the Holocene is the current geographical era, referring to the past 11,700 years of human history. None of those eruptions were VEI 8. The last super eruption was in New Zealand, nearly 30,000 years ago. Compare a Category 8 eruption, so massive it's labelled apocalyptic, to the eruption of Hungatonga Hunga Hapai in early 2022. The largest volcanic eruption in the 21st century, the eruption of Hunga Tonga Hunga Hapai, was still only a VEI 5 or 6. Atmospheric shockwaves swept across the globe, tsunamis reached as far as the Americas, and the sound of its eruption could be heard over 9,000 kilometers away in Yukon, Canada. And yet, despite the mass or wide-scale destruction, its eruption was nothing compared to a level 8. It's easy to see why then volcanoes capable of producing these immense monstrosities are labelled supervolcanoes. Yellowstone has experienced 3 such eruptions in the past millions of years. But supervolcano never originated as a scientific term, and while it has gained popularity and widespread use amongst the general public, many scientists don't use the word. The term supervolcano was first used in the 1940s by Howell Williams, who disproved a theory by geologist Edwin Hodge. Hodge believed that the Three Sisters volcanic region of central Oregon was not in fact 3 separate volcanoes, but rather a singular one that he dubbed Mount Multnomah. In his 1948 book discussing this, Howell Williams referred to this hypothesis as a supervolcano, and the term seems to have stuck. Scientist in charge of the Yellowstone Volcano Observatory, Michael Poland, is not a fan. In an article he wrote for the Caldera Chronicles, a series of articles about volcanism and geology in Yellowstone, Poland offered 3 main reasons for disliking the term. 1. It's trite, turning a complex aspect of volcanology into something catchy. 2. It's misleading, making it sound like supervolcanoes only ever have super eruptions. This is not true. Like any other volcano, so-called supervolcanoes can have a variety of eruptions. Not all are world-ending threats. 3. It's misapplied. Super eruptions are rated 8 on the Volcanic Explosivity Index, but volcanoes like Campi Flegrei, which have never had VEI 8 eruptions, are being called supervolcanoes. Instead, Poland suggests calling these volcanoes caldera systems. Eruptions with the enormous explosive power needed to rank at a level 8 on the Volcanic Explosivity Index create calderas. In suggesting this, he quotes his colleague Dr. Jamie Farrell, the chief seismologist of the Yellowstone Volcano Observatory. Dr. Farrell says there are no supervolcanoes, only volcanoes that have super eruptions. But Yellowstone has had super eruptions in the past. It's understandable to theorize that it might one day have a super eruption in the future. Fortunately, an eruption of that magnitude is a long way away. Beneath Yellowstone lies 2 bodies of magma, making up the reservoir that feeds the volcano. Though there hasn't been a magmatic eruption at Yellowstone in a very long time, there have been hydrothermal eruptions, and the Yellowstone Volcano Observatory considers it a high threat potential, based on the National Volcano Early Warning System. This warning system determines volcanic threat based on the qualitative risk of volcanic hazards to people and property. This risk is calculated by combining volcanic hazards, which are the dangerous natural phenomena produced by volcanoes, and the exposure of people and property to these hazards. Each individual volcano is assigned numerical values, ranking them based on their hazard and exposure factors. A volcano's threat level is the multiplied sum of these scores. The higher the threat level, the more robust the monitoring. For Wyoming, Yellowstone is listed as high priority and is monitored by the Yellowstone Volcano Observatory. Comprised of 9 state and federal bodies, the Yellowstone Volcano Observatory monitors and provides hazard assessments for volcanic, hydrothermal, and earthquake activity on the Yellowstone Plateau region. If Yellowstone were going to blow, we would know. As a species, we're obsessed with doomsday. From raining hellfire to the ground splitting open and swallowing us whole, the apocalypse seems ever present in pop culture. So, when the term supervolcano is thrown around in tandem with Yellowstone, it sets imaginations on fire. Given that the park draws millions of visitors each year, it's understandable that imminent fiery death is something occasionally entertained by the curious or morbid tourist. But how do we know that an eruption, at least of a world-ending magnitude, isn't likely to occur anytime soon? Before a volcanic eruption, there are signs. Increased seismic activity, gas emissions, ground deformation, and increased thermal activity. This increased thermal activity is vital, if sometimes difficult, to monitor. Anomalous thermal activity that is not usual, may not appear in thermal infrared images as increasing temperatures, but rather as an increased area of a static high temperature. So, it's important that scientists measure how much heat has radiated away over time. Heat, you see, is different to temperature. Temperature, whether measured in Celsius, Fahrenheit, or Kelvin, is a material property that something might have. A material, regardless of what it is, cannot have a heat the way it has a temperature. It can only gain or lose heat. Where temperature is a property, heat is the measure of change, and that heat can radiate away. Using a principle called the Stefan-Boltzmann law, scientists can calculate how much heat has radiated away. But it's not always that easy. What makes determining the rate of heat loss difficult is sunlight. Yellowstone National Park is a massive ecosystem, spanning thousands of kilometers. And it's outside. This may seem like an obvious point to make, but it's an important one. You see, when sunlight hits a surface, that surface gains heat, or heats up, as we would say in a normal everyday conversation. And as that surface absorbs sunlight, its temperature increases, showing on thermal images as a higher heat than surrounding areas. Sometimes even hotter than geothermal ones. But when monitoring thermal activity for volcanoes, the goal is to isolate the geothermal heat, the heat underground. So, scientists focus their analyses on satellite thermal infrared images taken at night. This reduces, but does not entirely eliminate, the effects of absorbed sunlight, allowing them to calculate more accurate readings. Thermal areas, as research geologist Dr. Richard Gregory Vaughan explains, are the surface expressions of a deeper magmatic system. These areas shift and change, heating up, cooling down, and even moving. Every thermal area in Yellowstone National Park has a defined nearby non-thermal area. These non-thermal areas have similar surface cover types, ranging from grassland, trees, and scrub steppe, and similar topography. The cover type and topography of the area affects how much sunlight is absorbed, aiding in these calculations. These thermal satellite images are important tools for monitoring volcanic activity, due to their ability to quantify subtle thermal characteristics of the landscape. Using data gathered over the years, researchers have been able to determine that, geothermally speaking, Yellowstone is neither heating up nor cooling down. While individual thermal areas will shift and change, fluctuating in shape, location, appearance, and temperature, the park as a whole has had a stable heat output over the years. This data, along with data taken from seismic stations, helps geologists and volcanologists at the Yellowstone Volcano Observatory to determine the likelihood of Yellowstone erupting. These seismic stations also give us a glimpse into what the Earth's molten veins look like deep underground. Roughly 2 by 4 meters, hundreds of these seismic stations were deployed throughout the park in 2020. Designed to have a low impact on the landscape, the stations are installed partially underground. Housed in a tank is a seismometer with a computer and communication equipment to transmit gathered data. These electronics are charged by a solar panel above ground, which also connects to an antenna and GPS receiver, allowing researchers to track exactly where each station is. Using data gathered by these stations over the course of up to 2 years, scientists are able to map the seismic wave speeds, and this allowed them to piece together an image of the magma system structure beneath Yellowstone. The results from this data, which were published by Wu et al., suggests that the top of the magma complex is characterized by sills, horizontally elongated areas of localized magma storage. As seismic waves travel through the Earth, they slow down depending on the composition and form of the rock they travel through. Seismic waves move more slowly through hot, molten rock, and the more seismic stations, the clearer the image. We now know that beneath Yellowstone lies 2 magma reservoirs, stacked on top of each other. The closest to the surface is a viscous rhyolite magma, between 5 and 19 kilometers deep. Just beneath this rhyolitic reservoir is another, holding a less viscous and more fluid basaltic magma, between 20 and 50 kilometers below the surface. But magma isn't the only thing to come from volcanoes. Older studies from the early 2000s looked at a tiny little crystal called a zircon. These volcanic crystals are capable of withstanding extreme heat and pressure, without their composition changing. In 1998, Ilya N. Bindman was a postdoctoral fellow, joining researcher John W. Valley as they studied Yellowstone zircons. What they found was surprising. 640,000 years ago, the youngest Yellowstone super-eruption created the lava creek tuff. But the zircons that Valley and Bindman analysed didn't match the expected oxygen composition of crystals that formed in deep, hot mantle. Instead, these crystals were depleted of oxygen-18, and must have originated in rock that once dwelled closer to their surface, as their composition suggested that they formed from rocks that had once interacted with precipitation, rain or snow. If rumblings of a new eruption were to begin, we would have anywhere between weeks to hundreds of years to prepare. The oxygen signature of the lava, Bindman explains, when compared to the ages of zircons, can reveal what type of magma may be forcing its way to the surface. If that magma is also depleted of oxygen-18, it is likely old, thick and sluggish remnants of an earlier explosion. But if the lava carries with it fresh magma and no old zircons, then an eruption of catastrophic scale is more likely, as a new volcanic cycle had begun. This, of course, is hypothetical. So what does this tell us about Yellowstone's inclination to erupt? Well, we know that it's not likely to erupt on a massive scale anytime soon. Generally speaking, the more immense an eruption, the less frequently it occurs. Volcanic Explosivity Index 7 eruptions tend to happen 1 or 2 times every 1,000 years or so, and these are 10 times smaller than level 8 eruptions on the Volcanic Explosivity Index. At a level 7, a volcano emits on average upwards of 100 cubic kilometers of pyroclastic deposits, while a level 8 can emit upwards of 1,000, and these occur roughly every few 100,000 years. But that doesn't stop speculation. A common, if misguided, argument is that because Yellowstone's last super eruption was 600,000 years ago, it's now overdue for another of a similar scale. If Yellowstone volcano were to erupt tomorrow, there would be global implications. Remember, Hunga Tonga Hunga Hapai was felt and heard around the world, and it was only a level 5 or a 6. But if Yellowstone were to erupt, we would know it was about to happen. The ground would rumble and shake for weeks or longer, the telltale warning signs of an imminent disaster. Intense, localized seismicity would be observed, with many earthquakes measuring above a magnitude 4 or 5, along with significant and noticeable uplift around the main caldera due to rising magma. This rising magma would cause explosions from geothermal reservoirs. Gas and ash would explode into the Earth's stratosphere, and the ground, now empty of magma and free from built-up pressure, would collapse in on itself, creating a new caldera. Devastating pyroclastic flows spread out from the newly formed caldera, devouring everything in their path, as they flow like volatile liquid across the landscape. Volcanic dust and ash would choke the sky, falling like snow and blotting out the sun, drenching the area in a poisonous dusk. Worldwide, airports, communications, and electricity would all grind to a halt. If the blast was large enough, its far-reaching effects could plunge the world into a volcanic winter, as sulfur aerosols shot into the atmosphere, reflect incoming solar radiation, and absorb terrestrial radiation. This would cause the climate to shift, the Earth's temperature to cool down. The good news is that this isn't very likely. A preliminary assessment of volcanic and hydrothermal hazards in Yellowstone National Park and its surroundings found that a geyser eruption or lava flow is the most likely. Remember, lava flows are lower on the volcanic explosivity index, and while still dangerous, are less destructive. This published assessment considers the probability of a super eruption to be negligible, less than 1 in a million. Despite the unlikelihood of a cataclysmic eruption, given the park's prominence, it's important to acknowledge that eruptions of this scale have happened in the past and will inevitably happen in the future. If Yellowstone were to erupt, the new caldera is more likely to appear northeast of the present caldera's center, as the continent continues to drift. The preliminary assessment repeatedly stresses that this occurrence is highly unlikely, and if Yellowstone were to explode, it would not do so in our lifetime. Our Earth operates on a timeline that is imperceptible to us mere humans. Geological ages are so massive that it's hard to conceptualize them, and though a few 100,000 years seems like an endless, terrifying age to us fleeting mortals, to the Earth, it's an afternoon nap. Yellowstone, in all its explosive glory, remains deep in slumber, though it tosses and turns now and then as geysers and geothermal vents shoot steam skywards. It shows no sign of waking. All that's left are the echoes of eruptions past.